Okay, so we continue with the next part, which is factorization, where we will look a bit more deeply into some of these techniques. So let's first try to get the high-level idea, the intuition of what factorization is. As we said, it's a representation that we want to construct directly from the database that ideally has a size that is very close to the original database size, but it represents all the query, the query results very efficiently. So how is that possible? How is it possible to have such a compact representation? Here's a nice analogy to think about. If I give you a graph, then by doing many traversals, you can compute all the paths here from left to right. So basically all the ABC paths in this graph. And of course, this can be exponentially many in some cases. And it's in general expensive to do this. Even in this small example, we have here on the left 18 edges and 9 nodes, while the paths are 27 and each one contains 3 nodes. But now let's suppose that the opposite happens, that I give you the paths instead of the graph. Well, then you can reverse the process and you can compact all the paths and represent them as this graph, which is much more compact. And that's what the idea of factorization is. The reason that it is possible is because of shared structure that a graph has, and it allows us to create representations that are exponentially more compact and also lossless, because we don't lose any of the paths. We can go back and forth between the representations at any time. As I hinted also in the introduction, there's a relationship between this and algebraic factorization of expressions. So, for example, here's an expression which has product and sum. And if you notice here, we have A1 appearing 3 times, A2 appearing 3 times. So what we can do is we can factorize it. We can pull out A1 plus A2, and we can rewrite this formula in this compact way. And in fact, this can be interpreted within this graph framework in the following way. On the left, we have paths, essentially, that go from A's to B's, right? So A1, B1, the product is just a path going from node A1 to B1. The process of factorization can be interpreted by as introducing this node in the middle, which forces different paths to share common edges and essentially creates the shared structure. And in general, it's more compact than the left one. So let's now try to apply this to a conjunctive query. Here's an example of a path query. So Ry joins with Sy, Sz joins with Tz. And here I'm just showing the connections are the joining tuples between the relations. And now let's try to represent this as a graph. So what we do here is we introduce one node for every tuple in the database. And so you can see that every relation essentially becomes a layer of nodes. And the edges between the tuples are the joining pairs. Now, the paths in this graph, if we start from left and go to right, are essentially the join results. But now, if you look closely at this, you will realize that if we have n tuples per relation and L relations, the size of this representation can be quadratic in n, it's n squared times L, because we can have very dense patterns here between 2 relations. And the question now is, can we lower this cost? And if the join pattern between the 2 relations is completely arbitrary, let's say it's a theta join with some arbitrary theta predicate, then no, it's not possible. But for equijoins in particular, we have a very regular pattern and we can exploit it. The way we exploit it is, again, by introducing nodes in the middle. Every node here represents a specific value of a column, here Y and here Z. And these intermediate nodes further factorize the representation. And by doing this transformation, essentially we build a representation of n times L, which is linear in the size of the database. Now we don't have to first construct the quadratic one and then go back to the linear one. We can construct the linear one from the beginning, and here's how it works. We start from the bottom up, from right to left here, and we build appropriate indexes for every relation. So here for T, we build the hash index that maps the Z values to the tuples of T. And for every value of Z in the hash table, we create an intermediate node, and we connect connect tuples. Then we scan S, and for each one, we look up in the hash table if there is a match, and we connect them also with those intermediate nodes, and we keep doing this bottom up until we reach the end. So that's how we construct it. Now, as we construct it, we can also remove the nodes that don't have any joins. Like if you look at, for example, here at 2.7, when we reached this, we figured out that there's no join, that it doesn't join with any tuple in T, so we can remove it. And then this also removes all the later nodes, which is essentially the same thing as the semi-join reduction that Wolfgang was talking about. So by building this representation, we are implicitly doing a semi-join reduction. Now, let's try to do the same thing for a query that has a tree structure. So that's the same example that Wolfgang was showing before with the Yanakakis example. And in order to build the representation, we have to follow the order of the join tree. So you can see the join tree here. U and W are the leaves here. And for each relation, we do the same thing as before. We create a layer of nodes where every node is a tuple of the relation. And we build the representation again, bottom up in the order of the join tree, and we remove all the tuples that don't have any matches, with the only difference now being with the tree that, for example, if you look at A4B6, it's joining with something on the left, but it's not joining with anything on the right. So when this happens, we delete the tuple because it has to join for all the branches. So that's our representation. And the nice thing about this is that it directly supports the enumeration that Wolfgang explained before. We can now do it directly on this representation. So what we do is basically we traverse this graph. We start here with A1, B1, and whenever we have a branch in the tree, we go left and right, and we traverse the representation and find the first join result. And to find the next one, we perform something similar to depth first search. So we go to the next one here, to the next one here, and when these are done, we go back and visit the next tuple. And so unranked enumeration without ranking works in this representation directly, and the advantage is that we don't need to do any lookups in our hash tables as we are doing the enumeration. We can simply follow the edges of the graph. Now, I also want to talk a bit about two different ways of constructing this representation. We saw already one of them, which is the tuple-level representation, and we call it a tuple-level representation because it uses the tuples as the nodes. There's also a dual perspective of that, which is to use the values of the attributes as the nodes instead of the tuples. So you can see here for the same example, I have drawn a representation that has as nodes the values of the attributes. Now, these types of representation have been very deeply studied by work on factorized databases, and there are some differences between this type of representation, which we call here attribute level, and tuple level representations. One difference is that instead of a join tree, you can see, for example, that we haven't followed a join tree order here. We have used what is called a D tree, which is a tree. Well, it's actually a forest here if you because it's disconnected. That has the variables as the nodes, and it connects them in a way such that dependent attributes need to be on the same path from roots to the leaf. So another difference is that in this type of representation, A1 here you can see it has been repeated twice. This never happens in the tuple-level representations. The reason here is that if you follow the example, B1 joins with only F2 from U, but B2 joins, if we follow this path, it joins both with F1 and F2. So because this layer now is in the middle, we have to decouple the A1 node, and that's why it appears twice. So that's another difference. So to summarize, there are some differences between the two representations, and there has been a lot of work on the attribute level factorizations on how to construct these representations directly with projections, with cycles, and also a lot of work beyond just what I showed you, unranked enumeration, but also doing enumeration with some lexicographic orders or directly supporting machine learning models directly on this representation, how to maintain these under updates. But for full acyclic queries, for example, the size of the representation of the two representations is the same. It's linear for both of them. So for the rest of the talk, we will keep focusing on the tuple-level factorizations because in some aspects they are easier to understand. And I think now I will pass it on to Wolfgang, who will talk more about dynamic programming.